Hi everyone, we're going to continue on with chapter 5, thermochemistry. So we talked about work, we talked about energy, and then we're going to talk even more about heat. But remember that energy is the ability to do work or to transfer heat. And then work is just going to be able to move some mass in some type of displacement. So I have to apply a force over a certain period or over a certain distance, and that's going to be called work. And work is going to be measured in joules. Energy is also measured in joules, and heat is also a form of energy, which again is going to be measured in joules. For work, we saw that definition as work is equal to force times displacement. So force is measured in newtons, and then our displacement is going to be measured in meters. So we said in class today that a newton meter is equal to a joule. So 1 Newton meter is equal to a joule. Okay, let's actually go back. The reason that I have a random baseball, I guess, picture on here is just because we know that in that picture, the baseball player is doing some amount of work on that baseball because his body is going to have to transfer energy from the muscles in his arms into his fingers into the ball. And so ultimately that's work done by the pitcher on the ball. Okay, so work is force times displacement. But what is heat? So I can have energy by doing work, or I can have energy by transferring heat. Heat will always work by having energy transferred from a warmer object to a cooler object. So energy is always going to be transferred from the hotter system to the cooler system. So, for example, when you have a couple of ice cubes in a glass of water, we know that the glass of water that may be at just room temperature is going to transfer its energy into those ice cubes, which then is what's going to cause those ice cubes to start to melt in that glass. So that's just heat flowing from a warmer object to a cooler object, and that will always hold true. We're going to define something called a system and then define something called the surroundings. So usually we think if we define the system as substances in the reaction, then we usually just think as everything else, either it be the temperature or some type of release of energy that's going to cause a change in the system. So we're going to have systems, we're going to have surroundings, and we want to know what's happening to the system. So if we're going back and thinking about the ice cubes in that glass of warmer water, let's say that my ice cubes are the system, and then everything else would be the surroundings. So the warm water would be the surroundings. Energy is going to leave from the surroundings and be supplied to the system to cause that system to increase in its temperature so it will gain or absorb energy, okay? If we think about two different types of energy, there's kinetic energy and then there's also potential energy. We can measure, kinetic energy is just energy of motion. We can measure it by finding 1/2 mv squared, m standing for mass, and then a v standing for the speed at which it's moving. If I asked you if speed increases, what would happen to kinetic energy? You would tell me that kinetic energy would also increase. So right now I have a woman who is on top of a hill. She has a very high potential energy because that's just her stored energy, but she doesn't have any kinetic energy because her speed would be 0. As she moves from the top of the hill and starts to go down the hill on her bike, her potential energy is going to be used up into forming kinetic energy, and that kinetic energy is going to increase as she continues to gain speed. Potential energy is a little bit different when we think about it in terms of chemistry or in terms of the atoms themselves. So we know that atoms move. We know that they have some type of kinetic energy, but they also have a potential energy, and potential energy is found in chemical bonds. That I really want us to know that potential energy is really found in chemical bonds. It is, in essence, just stored energy. So we know that potential energy is just that stored energy that an object can possess. But it's because of its chemical composition. And why does that arise? What do I even mean by that? So potential energy is just stored energy, and it arises because of attractions and repulsions, aka Coulombic attraction, that an object is going to experience in relation to another object. So if I'm thinking about, maybe if we just even go back to that last slide with the cyclist here, it's easy to think about potential converting into kinetic here because we just have that bike going down the hill. So we can see that this is at 0 speed, this is at 0 meters per second, and then obviously or clearly that has some type of speed. It's harder to see that on the potential energy side. So it's an inner conversion of energy because one's increasing and the other one is decreasing. But what would that look like on the atomic level? So we go back for potential energy to our Coulombic or lattice energy calculation. So we're going to have our electrostatic potential or our electrostatic energy or the energy of that attraction, aka Coulombic attraction, is equal to K times Q1 times Q2 over the distance that's separating them. So I have two charges or two atoms separated by a specific distance. So it's that attraction and how far apart they are. So we know that K is just that constant, so that really doesn't have anything to do with the electrostatic potential. Okay, so as the electrostatic potential goes to 0, if I'm looking at this graph right here, then I can see that my distance, my separation distance, is going to go pretty much to infinite. It's going to go become infinite. In other words, the 0 of electrostatic potential energy is going to be defined as infinite separation of charged particles. So if I continue to broaden out the distance between two charged particles, then ultimately they're not going to have very much attraction. So if I'm thinking about the distance that I have between Ryan Reynolds right now, it's a really large distance, so our attraction is going to be very small. So that separation distance is, because it's so large and because it could be infinite, is going to give me some type of Coulombic attraction that's going to be equal to 0, okay? Which makes sense. The more distance that's separating two particles, the less Coulombic attraction they're going to have. Okay, so that's what this part is showing right here. I can also see on this chart how it's going to behave, how two particles or two atoms are going to behave based on their charges and then also based on their separation distance. So I can see that if I have two like charges, I'm going to have some type of repulsion. So a smaller separation is going to give me a greater repulsion, versus a greater separation is going to give me less repulsion, so I'll have probably less Coulombic attraction there. Opposite charges, if I have two opposite charges, then we're going to have a smaller separation and a greater attraction, so my attraction should be greater there. And then if I have two oppositely charged particles and the attraction and the distance is larger, then I don't have as much attraction because of that distance separating them. But why are the opposite charges down here with a negative E value or energy value? And then why are the ones that are repelling with like charges up here as a positive value? That's because now we're taking into account not only the magnitude, but the sign of the charge. So two like charges are going to give me positive values for that Coulombic attraction, versus two oppositely charged particles are going to give me a negative charge or a negative energy for Coulombic attraction, okay? So anytime you see an electrostatic potential energy is negative, it's because it's between two oppositely charged particles. And then anytime that you see a positively charged Coulombic attraction, it's because it's between two like charges. So we have some type of repulsion there. Okay, so let's just sum that up maybe one more time. So we can see when the particles are like in their charge, they're going to repel. And so we have that repulsive force pushing them apart. And in that case, the energy is going to be positive. And as that repulsion pushes them farther apart, I'm going to increase the distance here, which is then going to lower the Coulombic attraction, okay? When particles have opposite signs or opposite charges, so there's an attraction, the energy is going to be negative. And as the particles start to become closer and closer, then I'm going to have a greater attraction, but it's going to be negative. It's going to be negative because they're oppositely charged, okay? Okay, so many substances will release chemical energy whenever they react. And that's just because that energy is due to that potential energy that's stored in the arrangement of their atoms. So when we react, we release some type of energy, and that's just because we have all of that built up energy in bonds. And then the energy that a substance possesses because of its temperature, we're going to call that thermal energy. And that's just associated with kinetic energy, but we'll get more into that in a little bit. As we talked about work, we said that work was force times a displacement, which force is measured in newtons, displacement's measured in meters, and that's equal to a joule. A joule is also equal to a kilogram meter squared per second squared. And we can derive that again if we didn't get that today before the bell rang. An older version of energy, so energy and work have the same unit. Okay, so energy and work are in joules. Heat is also going to be in joules. They're all just types of energy. An older non-SI unit that we use all the time are called calories, but notice that that's a little c. So the little c is not the same thing as the bigger calories that you're eating in food. So a calorie that you eat is with a capital C, and 1 calorie is equal to 1 kilocalorie, and then which then would be related to our lowercase calories there. So this is not the one we eat. Actually, these are going to be a lot more of these calories if we are consuming our food in bigger calories. So 1 little cal is going to be equal to 4.184 joules. You are given this number on your reference page for your AP test. I highly recommend that you just know this number off the top of your head, so that way you're not having to look it up, you just know it. So this is a number that you're going to use a ton throughout this chapter, as well as in, it's like chapter 18 or 19 in our book when we get to second semester. Okay, let's define a system versus the surroundings. If we think about a system and surroundings with chemical reactions, the reactants and the products are usually our system, and then the container and everything else is usually what we constitute as the surroundings. So the system includes the molecules that we want to study. So in this case, I have gas particles that are in this piston. The gas particles are what I'm going to call the system. There are 3 different types of systems. The first type of system is called an open system. The second type of system is called a closed system. And then the third type of system is called an isolated system. In an open system, that's one in which matter and energy can be exchanged easily with the surroundings. So I have my Starbucks cup sitting on the desk, but I don't have the lid on it. It's just, it's open to the surroundings. So some of the water that's in my cup can go out into the surroundings in the atmosphere, or some of the water, if I could get some water vapor, it could condense and go into my cup.
Mick Rizzo to the office, please. Mick Rizzo to the office.
So an open system is one in which matter and energy can be exchanged with the surroundings. The next type, number 2, was a closed system. Will you shut the door, please? A closed system, which is what we're going to probably focus on the most. That'll be the most common type that we will look at. is where we can have an exchange of energy, but we're not going to have an exchange of matter. So now I have my Starbucks cup, but I have the lid and that lid is completely covered. I couldn't take a drink out of it. It's a closed system because matter isn't going anywhere. The tea itself isn't going to leave the cup. But if I applied heat to the cup, then I could apply energy to that matter. So a closed system is where matter can't escape, but energy can still be transferred. Then our last one is an isolated system. And an isolated system is one in which neither energy nor matter could be exchanged with the surroundings. Okay, so we had open, closed. We let Ava in. We have open, we have closed, and then we have isolated, okay? So system is what we want to study, what we want to focus on, and then surroundings are going to be everything else. So in my case, my gas particles here are going to be my system, and then the piston is going to be everything else, my surroundings. Okay, I want to do this one together in class because on Monday I kind of want to review all of this, and then we'll do this one together because it's just applying some formulas that we can use and then talking about potential energy, okay? So let's go on to first law of thermodynamics. The first law of thermodynamics states that energy is neither created nor destroyed. So in other words, the total energy of the universe has to be constant. Total energy of the universe must remain constant. So if the system loses energy, the surroundings has to gain that energy that the system lost. Or vice versa. So if the system gained energy, then the surroundings must have lost that energy, okay? Oh. So this is the most important observation is just that energy is conserved, and that is known as the first law of thermodynamics. We're going to talk about several types of energy. So this first type of energy that we're going to focus on is called internal energy. And the internal energy of a system is the sum of all kinetic and potential energies of all components of the system. So internal energy is the sum of kinetic and potential together. And ultimately, we just call that E, which makes sense. It's the energy that is comprising both kinetic and potential. So sum of all energy, we call internal energy, and that's going to be symbolized as E. We're going to see an analogy to this here in just a second. Generally, we don't know a numerical value at a specific given moment of internal energy for a system. Usually we're just going to be concerned with the change in internal energy because kinetic and potential will constantly be in some type of fluctuation. So it's really hard to just measure at a specific moment or instantaneously what the internal energy is of a system. So we're going to focus on the change in internal energy. So let's imagine that we start with a system with an initial internal energy, and we're going to call that the initial internal energy. The system's going to undergo some change, which could involve some work. It could involve some type of heat. And then after the change, the final energy is going to be E final. So the change in internal energy is what we care about. We'll call that delta E. And we're going to find delta E by taking the final internal energy minus the initial internal energy. Okay, so the final minus the initial will give me delta E. In a chemical reaction, if we're thinking about a chemical reaction, then usually the initial state is going to refer to the reactant side, and then our final state is going to refer to our product side. So, for example, when hydrogen and oxygen react to form water, the system is going to end up losing energy to the surroundings. So because energy is lost from the system, the internal energy of the products is going to end up being less than the reactants. And the diagram that we see here is called an energy diagram. And it ends up just showing us ultimately what that sign for internal energy would be. So the initial state is hydrogen gas and oxygen gas. And when we form water, we're actually releasing energy, okay? So energy is released from the system to the surroundings during this reaction. So if I were to ask you a question like this, I may give you an energy diagram, and then I'm going to ask you, did the system gain energy or did the system lose energy? Or what was the change? What's the sign for the change in internal energy? And because that arrow is pointed down, if internal energy is increasing up the Y, and that arrow is pointed down, it's clearly losing energy. So it's releasing energy from system to surroundings. Okay, thermodynamic quantities such as change in internal energy have three parts. It's going to have a number, so we have some type of quantitative piece to all of these energies. So it's going to have a number, it's going to have a unit. If we're talking about energy, that unit's probably going to be joules. And it's also going to have a sign that signifies direction. So if it's negative, it means that the system is losing energy or releasing it. If it's positive, it means that the system has gained energy and the surroundings have lost it. Okay, so if we're looking at this energy diagram here, this is the initial state. If we gain energy, then the final is going to be larger than the initial. So this gain in energy is just meaning that final is going to be larger than the initial. So delta E then would be positive. If we start here at the initial, but we lose energy or release energy, then the final state, the product side, is going to be lower in energy than that reactant side, the initial. So in this case, delta E is going to be negative. We lost energy to the surroundings. Okay, so if, it's just doing it on its own. If delta E is greater than 0, that means that it's positive, it's absorbed energy, and we call this energy change endergonic. If delta E is less than 0, then it's negative, it has released energy to the surroundings, and we call this energy change exergonic. So releasing, exiting, absorbing, it's going into. So ender, into, release, exiting, exergonic, okay? We are going to stop here. We'll start here on, actually, someone remind me, we're starting here. We're going to start on this slide on Monday, and then we'll go back to where that little safe was. I hope you guys have a really wonderful weekend. I'm very proud of you on your Chapter 8-9 tests. FRQs are up in, will be up in progress book on Friday. Cakes. Bye, guys. I will see you on Monday.
Class.
Cakes.